welcome you all in this course on mechanical measurement systems. Today we will discuss about the flow measurement. In today's lecture, the topics to be covered are, first of all, I will give introduction to the flow measurement, and then we will discuss about the obstruction type of flow measurement. Obstruction type of flow meters, not flow measurement. Now, flow measurement is necessary in many of the engineering applications, right? Especially where heat transfer takes place, because we often calculate heat transfer, rate of heat transfer, mCp delta T. M is the mass flow rate, right? So it is always required in many of the applications like heat exchangers, right? And evaporators, condensers, even a power plant, there is a condenser where heat exchange takes place, and there is a boiler, economizer, and many places. I mean, not only in power plant, in air conditioning industries also, the mass flow rate measurement is required, right? Not for the working of air conditioner, but for the development of air conditioner, we need to have mass flow rate of refrigerant in the system. Likewise, in many of the engineering applications, not only in mechanical engineering applications, civil engineering applications, the mass flow rate is required. Transportation of the oil in the pipeline, mass flow rate is required. So flow measurement is a very important activity in all spheres of engineering application. And some of the applications, extreme precision is required. So that is also an issue where we just want to have the gross value of the flow rate, right? And some of the applications, very precise flow rate is required. For biological applications, from applications in the area of medicine or in the area of research, very precise flow rate is required to be metered. So selection of the instrument is governed by many parameters. And of course, cost is also one of the parameters. If we are not very much concerned about the accuracy, we will not like to go for a very high-end type of flow meter, right? There are many methods. There are a number of methods through which we can measure the flow rates. And the cheapest and the very reliable method of flow rate measurement is pitot tube. We will start with the basic device, pitot tube. You must have studied in fluid mechanics. When you want to have flow rate in a pipe, suppose I want to measure flow rate inside a pipe, I will use this method. From here, I will make a tap for static pressure. Here, I will make a tap for dynamic pressure, right? They will be connected through a U-tube. Dynamic pressure means stagnation pressure, and this we can calculate using Bernoulli's equation. Bernoulli's equation says that, suppose this is P1 and this is 2. So P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. If fluid is incompressible, if fluid is compressible, then definitely rho 1 and rho 2 will also come into the picture. But water we consider as an incompressible fluid, so the density remains constant. And here at the stagnation point, the velocity also turns to be 0. This is 0. So V1 is nothing but under root 2 times P2 minus P1 divided by rho. Now, if we are able to measure this P2 minus P1, the density is known to us. Now, P1 minus P2 is nothing but the pressure difference between point 2 and point 1. Now, this differential pressure can be measured with the help of there are many ways, but this is the simplest one. If there is a steady flow, if there is a fluctuation in the flow, then with the manometer it is a problem. Then we will have to go for some electronic device or for differential pressure measurement. But if it is a steady flow, then this pressure is high, right? So this pressure difference, this H pressure difference will give the pressure difference, and through this pressure difference we will be able to make the find the velocity in this pipe. Now suppose instead of a pipe there is a plate, and I want to have boundary layer thickness over the plate. So there is a plate and I want to have hydrodynamic boundary layer or variation of velocity in this direction, right? So what I am going to do in a streamlined flow, I will put the nose of pitot tube at different location. I will keep on moving in vertical direction. I will be getting different velocities. But in this case, for the measurement of static pressure, the design has to be a little modified. Here, there is going to be a nose for stagnation pressure, and it is covered by another tube, sorry, not tube, another layer of metal, and it has holes. Right, so it is a hole, and then it is coming this way, this side. Now here, this is filled with the static air. Suppose air is the media. This is filled with the static air. So here we will get static pressure. When air is blown over this tube, from here we will get static pressure. And from this point, we are going to get stagnation pressure. And if these two are again connected by a U-tube manometer, then this pressure difference will give the delta T. This is H. So this H will give the pressure difference or pressure difference between stagnation pressure and static pressure. Once the pressure difference is known, when the pressure difference between stagnation pressure and static pressure is known, we can calculate the velocity of fluid. Now in this case it is air. Now here there are certain scope of errors in the measurement. First of all, this part of the pitot tube has to be perfectly aligned with the streamline flow. If it is not aligned properly aligned with this flow or the flow of the fluid, in that case it is going to affect our output from the pitot tube. Now second thing is, when this pitot tube is used for the flow measurement in a pipe, same pitot tube, now it will occupy certain, this leg of the pitot tube will occupy certain cross section area of the tube, and that will increase the velocity, because what is it is doing? It is obstruction type of device, which is obstructing the flow over the flow of the fluid. So due to obstruction or due to reduction in the cross section area available for the flow of fluid, the velocity in the vicinity of this point will increase. The moment the velocity is increased, the static pressure will reduce. So in that case, if we draw the variation of static pressure with the length, suppose here we have nose of pitot tube. So initially stagnation pressure was 0, and at the nose it has increased. At the same time we will find a drop. It has increased pressure here, but at the same time, because available cross section area has reduced, it will be less than the static pressure. The static pressure will reduce. Now another obstruction in the flow is vertical column of the pitot tube. Now this column will again act as a bluff body, right? And stagnation of air will also take place here. So this reduction in pressure will die out after certain length, and at the same time, this stagnation pressure will also reduce when we move in this direction. This is the stagnation pressure created by the vertical leg of the pitot tube. So now at this point, they are going to neutralize each other, and exactly this should be the position of this point. So location of the point for the tap of static pressure is not arbitrary, and that is why you must have seen this arm or this leg of the pitot tube has sufficient length. We can make it like this also. We can make it like this also. So, I mean, as per the principles of fluid mechanics, it should work. But normally, this length is sufficiently long to neutralize the stagnation effect by this leg, and at the same time, this negative pressure is also compensated, right? And now after this pitot tube, we will take up another obstruction type of flow meter. And in fact, these type of flow meters are cheap and easily installed. That is, one of them is Venturi meter. Right? It also works on the principle Bernoulli's theorem, or it also works on Bernoulli's theorem. In Venturi meter, the flow meter, physically the flow meter appears to be like this, right? There is an upstream pipe and there is a downstream pipe also of constant cross section, right? Now what we do, we take one tap from here and one tap from here, because there is going to be a pressure difference between this point and this point. Because this point, the cross section area has reduced, this has caused the increase in velocity, right? And due to this increase in velocity, the static pressure has reduced in comparison to the static pressure at this point. Now let us take Bernoulli's theorem for 2 points, 1 and 2. We'll always write like this: P1 by rho 1 plus V1 square by 2 plus, because they are in the same plane, so potential energy we are assuming to be constant, it is not varying, is equal to P2 by rho 2 plus V2 square by 2. Now, if it is a incompressible fluid, then rho 1 is equal to rho 2, and if it is compressible, then rho 1 and rho 2 are different. Now, here also what we do, we simply take the help of this equation and we calculate the value of P1 minus P2, because P2 has reduced. So, P1 minus P2 divided by rho is equal to V2 square minus V1 square by 2. Now, velocity through a constant cross section, velocity, if you multiply velocity with area VA and rho, it will give you the mass flow rate, right? So, this velocity, or when we can say V1A1 is equal to V2A2, because mass flow rate is constant, density is constant. So, for any 2 points, the product of velocity and the cross section area is constant. Now, from here we can take the value of V1 is equal to A2 by A1 multiplied by V1, sorry, V2. Now, this value of V2 can be substituted here, and then we will get delta P, we will write delta P by rho is equal to V2 square minus A2 square V2 square by A1 square multiplied by 2. Sorry, this is whole divided by 2. Now, here delta P we have already calculated when we just not calc, we have already determined when we measured the static pressure difference between these 2 points using a U-tube manometer. So delta P is with us, area A1 and A2, these values are with us, then easily we can find the velocity of fluid in the venturi, and this velocity can be written as V2 is equal to C V2 is equal to 1 by under root 1 minus A2 by A1 whole square under root 2 delta P by rho. Delta P is P1 minus P2. So this is how we have calculated, because this V2 will come out 1 minus A2 by A1 whole square, this will go down, right, and delta P by rho multiplied by 2. Now this is the velocity, and if you want to have the volumetric flow rate Q, and the Q is going to be this multiplied by area 2. This will give the Q, volumetric flow rate. And if you further multiply this by density, you will get the mass flow rate. Now here the issue is, first of all, the flow has to be a stable flow. So upstream side, I'll rub this off. Upstream side of the venturimeter, the upstream side of the venturimeter, it has to be around 5 to 10 times of the diameter. Suppose this diameter is 1 inch. So upstream side has to be around 10-inch length without any change in the diameter, right? So it has to be stabilized and stabilized and the fully developed flow, and the converge angle, in order to reduce the losses, the converge angle has to be 21 degree plus minus, you can take 1 degree or 2 degree. 21 degree plus minus 2 degree has to be angle of convergence. Diverging angle has to be lower. Diverging angle has to be 5 to 7 degree plus minus 1 degree. Now why diverging angle is less than the converging angle? The diverging angle has to be less than the converging angle, because when in the diverging angle there is a tendency of fluid boundary layer to get separated from the surface of the passage. If so happens, there are going to be losses. There are going to be losses here, pressure losses here, which are not accepted. So that is why in most of the nozzles, whether they are used for some other application, in nozzles, the converging passage, the length of the converging passage is much less than the length of the diverging passage. Now, this diameter also, we have to ensure that it should be, the throat diameter has to be in a range of 50% to 25%, not less than 25%. Now, because what happens, when the fluid enters the passage, right? In that case, vena contracta is formed. Vena contracta is formed. It means the actual cross section is this one only. So actual available cross section area is less than the available cross section area. So that is why coefficient of discharge is also taken into account. Coefficient of discharge takes place of this loss due to formation of vena contracta and other losses due to friction and all. So, all the pressure, all the losses are covered under this coefficient of discharge. So, actual discharge, because whatever we are calculating from here, the actual discharge is less than this, and for venturimeter it is around 0.8, CD it ranges between 0.8 to 0.9. It can be 0.7 also, that depends upon the design of the venturimeter. So, benefit of this type is of obstruction type of instrument is high recovery. Recovery is high, I mean the pressure recovery is because CD is, let us say 0.8. If you compare the CD of orifice meter, I will discuss the orifice meter also, it is quite high. It has well established characteristics. Okay. Clogging problem is not there because passage is has sufficient diameter. So, clogging problem in such type of flow meters is not there, and they are easy to install, and they can be installed at any angle. I mean not only in horizontal direction, they can be installed in vertical direction, they can be installed at an inclined angle also, at a certain angle also, right. So, that is one type of obstruction type of flow meter. Another type of obstruction type of flow meter is orifice meter. Now, in orifice meter, there is no converging or diverging passage. There is a plate which has a circular orifice in the middle, right, and working principle is same. Pressure, static pressure here, because here there is going to be a fall in the static pressure, but in this case, and then we take the delta P. I think these instruments you must have studied in the classes of fluid mechanics also. That is why I am discussing in brief. I am not going into the details. In orifice meter, the benefit is we can go for a larger diameter. Even we can go for a diameter of 2 feet. I mean of 75 centimeter, even 100 centimeter diameter tube. We can put, what we have to do is we have to simply put a plate with a orifice in the middle. So, for large diameter tube flow, orifice meter is good, but it is an obstruction type of device and pressure recovery is poor, pressure loss is high, and the coefficient of discharge may be as low as 0.3. So, it also depends upon the design of the, normally for a small diameter instruments which are obstruction type, they are made of brass, right, because brass has a smooth surface, so losses due to friction are less. But if we have to go for a large diameter, then we have to go for other material for the fabrication of this type of instrument. There is another instrument which is known as sonic nozzle. In sonic nozzle, in the tube there is a nozzle. Rest of the theory is same. A nozzle is fitted and then again there is pressure loss and difference in head, and then again, but sonic nozzle is a compromise between the venturimeter and the orifice meter, and sonic nozzle is normally used for the gas flow. Because when we talk about the gas flow, in that case, the density of the fluid, the change in the density of the fluid has to be taken into account. And in this sonic flow, pressure is approximately 80 to 90% of differential pressure. So, pressure recovery is not very high, very good in the sonic nozzle, but it is better than the orifice meter or it is between orifice meter and the venturimeter. It is cheaper than the venturimeter, right. Now, so far we discussed about the fluid which is incompressible. Suppose fluid is compressible, because we have to measure, many times we have to measure the flow of the gas as well. And for the gas flow also, this orifice meter and the venturimeter are used. They are not specifically used for the water or the incompressible liquid. They are used for the compressible liquid as well. But in case of compressible liquid, the governing equation will change. Now governing equation, earlier we were writing for incompressible fluid as P1 by rho plus V1 square by 2 is equal to P2 by rho plus V2 square by 2. Right? Now, this equation is a if you compare this equation with the first law for open system, first law for open system is H1 plus V1 square by 2 plus Z1 is equal to H2 plus V2 square by 2 Z2. Huh? V2 square by 2 plus Z2. Now here in the first law, now this is horizontal, so this we will always consider 0 because, right. Now in the first law, if you take a specific case of first law, now this is, now I will write it again. The first law for open system is H2 minus H1 plus V2 square minus V1 square by 2 plus G Z2 minus Z1. Right? Now this is first law for open system, and this is equal to Q minus W, or delta Q minus delta W. Or if you want to write in differential form, then dH is equal to V dV plus G dZ is equal to del Q minus del W. Now, in fluid flow, there is no heat transfer, right? So, heat transfer is 0, work is also 0, there is no movement of the boundary of the system. Now, we have H2 minus H1, V2 minus E square minus V1 square by 2, G Z2 minus Z1 is equal to 0. If it is horizontally installed, then this is also 0. If the measuring instrument is not horizontally installed, as I said in the case of venturimeter, it can be installed vertically. When the venturimeter is installed vertically, then this will also come into the picture. The same formula cannot be used. Then we have to derive from the basics what is going to be the pressure difference between these two, and this, and how much is pressure due to static pressure generated due to change in the elevation. That has to be taken into account, right? So for here we assume that it is 0. So H2 minus H1 plus V2 square minus V1 square is equal to 0. So or H2 plus V2 square by 2 is equal to H1 plus V1 square by 2. We always know that H is equal to U plus PV. So this equation we can always write U1 plus P1 by rho. Now why we are writing P1 by rho? Because V is 1 by rho. Here it is a specific enthalpy. So this is a specific volume, meter cube per kg. So it is going to be 1 by rho plus V2 square by 2 is equal to U2 plus P2 by, this is rho 1 and this is rho 2 because it is compressible. Just a minute. We'll write U2 plus P2 by rho 2 plus V2 square by 2 is equal to U1 plus P1 by rho plus V1 square by 2. Fine. Now this can always be written like this when there is a change in density. Now if there is no change in density, right, then U2 and U1, these terms are, because it is now then and they are neutralized. But since there is a change in density, it means compression or expansion has taken place, right? Now, if we take U2 and U1 into consideration, Then U1 minus U2 is equal to Cp T1, sorry, CV T1 minus T2. And CV T1 minus T2 is R by gamma minus 1 T1 minus T2. Right? So U1 minus U2 is equal to 1 by gamma minus 1 RT1. If you use ideal gas equation, we are assuming that ideal gas is flowing inside the tube. So RT1 is equal to P1 V1. RT1 is equal to P1 V1 or RT1 is equal to P1 by rho. Because V1 is a specific volume, it is in meter cube per kg and this density is kg per meter cube. So then P1 by rho 1 minus P2 by rho 2. Now this, because P1 and P2 we are already measuring. So this will also be incorporated in the final expression, this phenomena, and we'll get the expression as V2 square minus V1 square by 2 is equal to P1 by rho 1 minus P2 by rho 2 plus 1 by gamma minus 1 P1 by rho 1 minus P2 by rho 2. This expression, because this is due to U1 and minus U2. Now, if we take this out, we will get gamma over gamma minus 1 P1 by rho 1 minus P2 by rho 2. If we take 1 plus, because if we take this P1 by rho 1 minus P2 by rho 2 common, we will be getting 1 plus 1 by gamma minus 1, then gamma minus 1 plus 1 divided by gamma minus 1, then gamma over gamma minus 1. So that expression has come here. Now, what is remaining is finding out the value of V2, and again we will use the same relation of continuity equation. Rho 1 A1 V1 is equal to rho 2 A2 V2. Here density will also come into account. So rho 1 A1 V1 is V is velocity, rho 2 A2 V2. Right? Now using this equation, the final expression can be written as V2 is equal to under root 2 gamma over gamma minus 1 multiplied by P1 by rho 1, 1 minus P2 by P1 raised to power gamma minus 1 over gamma divided by under root 1 minus A2 by A1 whole square multiplied by rho 2 by rho 1 whole square. Right? So there is going to be an alteration in the expression of V2 when we take compressibility of the working fluid into account. Right? So there are going to be two different equations, one for incompressible fluid and another is for compressible fluid, but working principle is same. We simply take difference between stagnation pressure and static pressure, and this pressure head difference in this energy is assumed to be the kinetic energy, change in the kinetic energy of the fluid. We work on based on this principle, all these three instruments, now 4 instruments, pitot tube, venturi meter and orifice meter and this sonic nozzle, they work on this principle. This is all for today. In the next class, we will take up some more flow meters for the discussions. Thank you.